Hi everyone, welcome to my channel to learn algorithm with me together. Today let's take a look at 1650, lowest common ancestor of a binary tree 3. And what is this problem talking about? We will be given two nodes of a binary tree P and Q, and then return their lowest common ancestor LCA. And each node will have a references to its parent node, and the definition node will right like below, right? And what first of all, what is the lowest common ancestors? It means that is the common ancestor of the two nodes P and Q in a tree. And for example, like here, we have the tree looks like 3, 5, 1, 6, 2, 0, 8, and then 7 and 4. Now, if we want to have the node is P equals 2, 5, and also 1, the lowest common ancestor is just exactly 3. Or if we want to know like the node 6 and 4, and for example, we need to know the previous ancestor of 4 will be 2, 5, and 6 is also have like 5, so their lowest one will be 5. And probably we can write the path of it is like how we like get from the root node to a tree, like 3 to 5, and then to 2, and then 4. So 4 is exactly what we want. And how about to 6? 6 will be 3 to 5 to 6. So 6 is also another one we want. And now the lowest common ancestor, the common ancestors will be like 3 and 5. But the lowest one will be like 5, which is the most closest to the target node we want, like 4 and 6. So now we want to like get like this one, the lowest common ancestors. And now we need to know like yes, we know the input is only have the node P and Q. And other than that, we have no more information. Here we only know probably one more is parents, right? So now how we solve this problem? If we only know like the nodes we want like P and Q, and yeah, that's the problem, how we solve this. If you already done probably another problem, I remember there's a linked list problem. It also want us to find the intersection of two linked lists, right? And this problem can convert it to that problem. So I believe that problem is something like, if we know we have two linked lists and they have intersection. So first of all, we have the linked list from this one, and another linked list is like this. So the problem comes out to be like, we find here is the node 3, and then pointed to 5, and then one is pointed to 6, another one is pointed to 2 and 4, right? And now because we know only these two nodes, 6 and 4, and we need to find the intersection of them. So how we get this? This is, I remember, there's a kind of linked list problem we need to solve. And this will be one situation. Another situation, like if the nodes is not like probably not the same size, and they will be like for example, like if it's still 3, 3, 5, 6, 2, 7, 4, and also 1, 0, 8. Alright, so this is the most common situation. We probably have 2 more, and let's have it here. Right, so what if like the P is here, the P is here, and the Q is here, or something like P is here or Q is here. Of course, the PQ can switch their places. So no matter what, we are still solving the problem something like here. Like this is one linked list and another one is here, and one linked list is like this here, and another one is going to this way. So no matter what, like for the second case here, let's move it to here. So this is the first one we traversed it to like to linked list. And for the second cases, it's also we have it like starting from the root node is 3, and then 1 is to 5, and continue to 6, and then we need to find their lowest common is here. And also for this one is the first is 3 as well, and then go to 5, 2, 4, and also the target node will be like 5 and 4, and the lowest common will be here. So no matter which, we are just solving like find the first intersection of these two linked lists. And then how we solve this problem, right? If you already done that, like finding the intersection of two linked lists, probably you already know how to solve that. But for this one, like now I can briefly to explain you. We are assuming that, well, we can have the distance like this will be the L1 distance. Or probably we can just say from the intersection point to here, this could be the L1 intersection, L1 distance, and from the intersection of 5 to 4, this distance will be L2, and for this part it will be L3. And now, because we already know the P and Q is here, right? We can use another pointer to mean them. Like this is we have 2 pointers, like saying that is P helper, and this is the Q helper. Yeah, it's not that clear, so this will be the P helper, and this will be the Q helper here. And now we can make it like, because we can always to reach out to its parent node, right? So this pointer will go to its parent node. So the distance it goes already like L1, and also it can also go to one step to its parent node. And after that, it also goes to its parent node, like it goes to the root node, and this one is also go to here. And after that, this one will move not going back to the P, it will go to the Q. Why we doing that is I want to like make the pH go through this way, is it goes through the L1 distance and then goes through L3 distance and then goes through L2, right? After it go to this side, and it will definitely like go to this intersection point, and also the QH is the road will be like go to L2 and move to L3, and then I move it not going back to Q, I move it to the P, so it will go to L1 again. So for these two roads, they are exactly the same. It means that they will definitely to meet at the intersection point here, because they are going through the exactly same distance and they use the exactly the same time. So this is kind of like the mating problem, something like that. And this is the idea of how I found the intersection node here, and how I write the pseudocode, right? First, I will have this helper node here. We can have the list node like the P helper and also the Q helper. They are all starting from where? Starting from the original, like P and Q helper is starting from Q, something like that. And while they are not made, because anyway they will just meet in the end. While if they will finally meet in the end if they are truly have the intersection, right? So while the pH is not equal to QH, what they're gonna do is like it will go to its parent nodes. This is what we got from the information it provides, and QH is also go to its parent nodes. But the point is, if they are already at a root node, in the next step they will definitely move to a null, right? So I mean, if they're already at the root node, this will point to null. So if the next one is null, they will just move to, I mean, if there is null, if the for the P helper go to the null, it will move to the Q, right? So now we can say that pH only move to its parent nodes when it's not at the null. So if the pH equals to at the parent nodes, right, it will go to it will not go to the, it's not parent node, it will go to the Q, otherwise it will go to the parent nodes. And same does the QH. If you already reach to the root node, right, it will go to the parent, go to another node P. And while doing this, they'll finally meet. When they are meet, we just return any one of them, like QH or PH, that's the fun. So now let's take this example, go through it. Like this is the QH and PH, and at the starting point, at first we'll move one step, and he also could move one step, and then move another step to PH and move another step. Oh wait, this is where it goes. And move another step here, move another step. So now once the pH goes to the root node, and what is the next step is goes to the Q starting point, and it goes to the next node. And after that, the PH will move to next node, and he will also go to the Q. P and PH will go to the intersection point, and he's also moved to the intersection point. So that's great. This code is already told us how to do that. And now we are checking some corner case, right? What if like the intersection point will be the root node, right? 6, and here is we only have like 2. And now let's have this. This is Q. Probably we can have P here, Q here, QH here, and PH here. And now we are moving it again, PH, QH, and move it PH, Q here, P here, and PH move to here, move to the Q, and QH move 1, and PH move 1, QH move 1, they meet, finally meet. Great, that works. And even though they are at the same, right? And now they will be like, this is Q, this is P. The Q will move 1, and P will move 1 as well, and Q move 1, P move 1, Q move to Q, and then Q move to H, P move to H, the intersection point as well. Great, so they meet. And this is how I solve this problem. And what is the time complexity? So the time complexity will be like, we only go through, this is the distance. They are exactly the same, so this is time consuming. So it means that it will be like OL, and L means from the P node to the road, here, the distance is the P node to the intersection point, and then intersection to node, and then the Q node to the intersection part. So this is the distance and the nodes we will have. And how about the space? We only use like 2 helper nodes to help us, so we can assume that just constant time. So that's pretty much. And now let's move to the coding part. And here we will first have the list node, the node helper, P helper, and or just P helper, and equals to P, and the Q helper equals to Q. And while they are not meet, P helper now equal to Q helper. And then what we're gonna do is the PH will move to the next point, but we have to confirm that the PH is not at the root node. Oh, here we have no idea the root node. So it means that we are still have to move to a non-pointer, right? So if PH equals to none, it means that it already moved to here. Wait, the Q start from here, the P from here. 1, 2, 3. You move to non-pointer. 1, 2, 3, and it will move to Q. And here it will move 1, and then move 1 here, move 1 here. They will still meet here. Great. But what if they are at the root nodes? Let me check. PH, QH, and here 1 here, move 1, and then to the non-pointer, move 1, and here to the non-pointer, and meet here, move here, move here. Great, they are still meet together, so there's no concern now. And if there equals at now, we move to the queue, or we just move to their parent nodes. And how about the queue helper? If I'll move, we will have to check whether it at the noun pointer now. No, if it is, we move to PL, or we will just move to its parent node. And after that, they will definitely meet together. So when they are meet, just return the PH or QH. That's fine. In our electronic, cool. So all the test cases passed, and we can also submit it. Cool. So yeah, all the test cases passed. So this is the how I solve this problem. We can convert this tree like to linked list, and they have some point they have some intersection point. And now the goal is how we find this intersection point. We use two pointers and make it to like go through the same distance, and they finally will meet at the same point. So this is how I solve this problem. If you think this video helps you, please give me a thumbs up. That would be great encouragement for me. And thanks for watching. See you at next video. Bye.